In this section, we're going to continue working with Taylor series, but specifically we're going to be looking at some applications. Now, the table that you see below is pulled from some of the homework sets that you'll see in my math lab. And it's basically a summary of all the Taylor series that you should be able to find using methods in the previous sections that we've looked at. So again, it's a summary. If you were asked to, let's say, find the Taylor series for this function centered at 0, you would be able to come up with this series and then this summation notation to describe that. Each of these you should be able to come with on your own. We're going to be looking at these and using these as applications in this section, so we'll just want to be able to refer to them very quickly. But again, on the exam and on your handwritten homework, you should be able to come up with each of these on your own. The first example that I want to look at when we're talking about working with Taylor series is using Taylor series to evaluate limits. Now, when we're using series to evaluate limits, you have to use a series as the directions indicate. So first of all, you can find limits other ways, but if the question specifically says to use series to evaluate a limit, then that's what you need to do. That's what you'll be graded on. So when we say to use series to evaluate limits, we could be looking at the limit, let's say, as k, well, let's do x in this particular case. X approaches 0, e to the x minus the quantity 1 plus x all over 8x squared. Now, we could plug x goes to 0 directly in. You'd have e to the 0 is 1, 1 minus 1 is 0, 0 minus 0 is 0 over 0. This would be indeterminate L'Hopital's. And then, of course, indeterminate L'Hopital's, I would take derivatives and kind of keep going from there. But I can't use L'Hopital's here, I need to use series. So what we do is we look at this and we say, okay, there's a function here, e to the x. And this function, e to the x, if I look up here, can be represented by this series. I'm not focusing on the summation notation here, I'm looking at the pattern. So what I do is I substitute that back in down here. So from here we know e to the x is equal to 1 plus x squared over 2 factorial. I'll plug in a few more of these following that same pattern, x4 over the 4 factorial, and then this continues on indefinitely. So what we're going to do here then is, in place of this e to the x, I will plug in this series. Now let's say this had been e to the 2x right here in this exponent. Then everywhere there's an x, I would just replace with a 2. This would be 2x quantity squared, 2x quantity cubed. Okay, so that would be the big difference there. So as I'm rewriting this, this would be the limit then as x approaches 0. And in place of the e to the x, I now put 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. And then I'll have minus the quantity 1 plus x all over 8x squared. Now what we're going to have to do is to simplify this quite a bit. Now you might look at this and say, well, wait, how can I simplify this? Because technically, and I should include this, this goes on forever indefinitely. But again, the whole idea is that we see a pattern. So the limit as x approaches 0, so I'll have 1 plus x squared over 2 factorial, but 2 factorial is just 2, plus x cubed over 3 factorial, but 3 factorial is 3 times 2, which is 6, plus x to the 4 over 4 factorial, but 4 factorial is 4 times 3 is 12, times 2 is 24. So this pattern continues, and then I take this negative and I distribute it, and I have minus 1 minus x, and this is all over 8x squared. Well, we have some things that'll cancel, 1 and a minus 1, x and a minus x. And then I also know that when we divide by a fraction, you multiply by the reciprocal. So this would leave me with x squared over 8 times 2 is 16x squared. X cubed, 6 times 8 is 48x squared. X to the 4th over 24 times 8 would be 96, would be 192x squared. Whoops, 192. Okay, and then this continues on indefinitely. Simplify it one more step. We have the limit as x approaches 0. This x words cancel. I'm left with 1 over 16 plus x over 48 plus x squared over 192. And then we have some sort of a pattern. Now what we notice with this pattern, as this goes out toward infinity, my powers of x are increasing, x squared, x cubed, x to the fourth. And then in my powers, not even my powers, but my terms in my denominator are just constants. So each one of these terms goes to 0 and will continue to go to 0. And I'm just left with 1 over 16 because the limit of a constant is a constant. So that is my limit. That's using Taylor series to evaluate a quick limit. Now we could have done the same thing with L'Hopital's, but again, if directions are specific and they say to use series, you need to make sure you use a series. As a side note, you're welcome to use L'Hopital's to check your work. You can also use Taylor series to differentiate a function as well. For this example, let's go ahead and look at the function f of x equals sine x to the fourth. Now we're going to do 3 different things with this function, but we're going to start with differentiating the Taylor series for this function about 0. And if we wanted to say the Taylor series about 0, that would mean the center was 0. So we could also say the Maclaurin series, because remember, a Maclaurin is a Taylor series centered at 0. And this will be for this function f of x equals sine x to the fourth. Now we're going to do a couple other things like I said, but let's just go ahead and start with this one. So what we'll do is we'll go up top and we'll find the sine function series. And remember, we're using the shortcuts for this particular section, but you should be able to come up with this same series by hand that we're just highlighting right here, because that's what we did in the first 3 sections. So even though we're kind of taking that shortcut and using a series that's given to us, you should be able to come up with the same series on your own. So what we want to do is we want to look at this series. This is what sine x is equal to, but we have sine x to the fourth. So in place of each one of these x's, we need to put an x to the fourth. So our f of x would be sine x to the fourth, which would be x to the fourth, that would go here, minus x to the fourth cubed over 3 factorial, plus x to the fourth to the fifth over 5 factorial, minus x to the fourth to the seventh over 7 factorial. And of course this continues on in the same pattern. Now what we'll want to do is simplify this and then differentiate. So we have f of x equals x to the fourth minus x to the 12th over 3 factorial. And I'm going to leave this in factorial form. I'm not going to rewrite this as 6 because hopefully we'll start to see a pattern, the 3, 5, 7, the odd, and help develop that pattern. X to the 20th over 5 factorial and x to the 28th over 7 factorial. Now this same pattern continues, so I have the dot, dot, dot. Now when I look at this particular function and I start to differentiate it, I just go ahead and use the old power rule that we're used to. So this would be 4x cubed minus 12x to the 11th over 3 factorial plus 20x to the 19th over 5 factorial minus 28x to the 27th over 7 factorial. And of course this continues on in that pattern. Okay, simplifying. Now when we think about simplifying, I'm going to write out these factorials. 3 factorial is 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1. And then 7 factorial, you get the idea, 7 times 6 times 5 times 4 times 3 times 2 times 1. Now we want a pattern here. We're looking for patterns. So I see that if I take 3 times 2 is 6, that divides into 12. And I'm just left with a 1 in the denominator. But over here, if I take 5 times 4, it divides into 20. I'm left with 3 times 2 times 1, which is 1 factorial. And then over here with 28, I would need to take the 7 and the 4 and that doesn't leave me with a nice factorial. So what I want to do is to always be left with a factorial in the denominator. So I'm just going to divide the first term of each of the factorials into the exponent for starters. And as I do that, I see, oh, I have a 4. And I'm always left with the factorial. 2 factorial, 4 factorial, 6 factorial. Okay, now from here, as I rewrite this, I can start to see kind of a pattern emerge. So this would be minus 4x to the 11th over 2 factorial plus 4x to the 19th over 4 factorial minus 4x to the 27th over 6 factorial. Now if I would have divided out more than just the first term, I wouldn't have been left with this nice pattern in the denominator. So what I can do from here is I can keep simplifying and then try and write this in series notation to try and figure out what this matches. So if I notice there's a 4 that's constant and there's also an x cubed that's constant to each term. So if I factor out a 4x cubed, I'm left with a 1 minus, factor out the 4, and x cubed, I'm left with x to the 8th over 2 factorial. Factor out the 4, x cubed would be x to the 16th over 4 factorial minus x to the 24th over 6 factorial. And again, I should have this plus dot 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 on all of these because this pattern continues. So as I'm rewriting this, I'm trying to get this to fit a form. And this looks like it really could fit a form. 2 factorial, 2, 4, 6 factorial. So let's see if we can get this to match up with something up above. So I definitely will start out at k equals 0 and to infinity. It's alternating, so I have to have an alternating piece. It looks like it starts out with 1 factorial, 2, 4, 6, but 1 factorial is 1, but so is 0 factorial. So if I start off with this as 2k, I think I'll get that progression that I'm looking for in the denominator. And in my exponent here, I need to start out with 0. For my x to the 0 is 1. So 0, 8, 16, 24. These are multiples of 8. So this looks like to me I could take this and rewrite it in terms of, I think we could probably do x to the 8k maybe. Let's try that. Multiples of k. And then negative 1 to the k is the alternating part. Now again, as I look through this, I'm trying to get it to fit from up above. This part, 4x cubed, I drag along, but this part is what I'm trying to get to fit something. Now from up above, you can go ahead and look through that, and if you do, you'll notice I never have an 8k, but I do have a 2k. So let's go up here and look for a 2k, and that's right here for this term. There's a 2k here, which I think would work. So I'm going to take this cosine of x, and that's what I think I'm going to try and make this match. Now I'm pretty sure I can make it match. And I just have to rewrite it a bit. Okay, so this looks like a good match. The only thing I want to be able to do is to take this x and then rewrite it to a 2k power, and then this will fit perfect. Well, this would be x to the 4th, and then I would have 4 times 2k is 8k, and then this would match my x to the 4th to the 2k. So this would be true for cosine of x to the 4th. So for x to the 4th, this would look like k equals 0 to infinity, and I get the x to the 4th from right here. Negative 1 to the k, x to the 4th to the 2k, all over the quantity 2k factorial. Now again, when I'm looking at this, I can see that this matches just with that quick little substitution. So this entire piece right here is just cosine x to the 4th. Okay, and that comes from here. So f prime of x equals 4x cubed cosine x to the 4th. So That's using series. Now we can check this real quick as well because we have other ways of finding derivatives. Our original function f of x was sine x to the fourth. F prime of x would be the derivative of the sine of x is the cosine of the argument. So the cosine of u times the derivative of u, or the derivative of the argument. So this is cosine x to the fourth times 4x cubed, and then I pull that 4x cubed out front, so 4x cubed cosine x to the fourth. Perfect. So this is my derivative, and you can see here that it checks. So that's the process of using Taylor series to help us find derivatives. Now with the same problem, let's go ahead and keep working on that. I would like to find the interval of convergence. And I'm going to use that for the derivative. So find the interval of convergence. For the derivative power series. So if you remember, the power series that we're looking at here would be f prime of x equals 4x cubed, and I'm using the series notation, k equals 0 to infinity, negative 1 to the k, x to the fourth to the 2k, all over quantity 2k factorial. So I'm using the series notation here because in order to find the interval of convergence, meaning I'm saying which, what is the best part here that does a good job at estimating, I need to use the ratio test. So I'm testing this on the series. Now for the ratio test, I take the limit as k approaches infinity of the absolute value of the next term. Now I don't have to worry about this negative 1 because I'm taking the absolute value. So this would be x. Now this is 4 times 2 is 8k, and so in place of that k I'd put a k plus 1 all over 2 times k plus 1 quantity factorial, that's my next term, divided by my current term. When you divide by a fraction you multiply by the reciprocal, and this is what I want to simplify. So this would be x to the 8k times x to the 8th, because we would distribute the 8. Now 2 times k plus 1, it's the quantity k plus 1, so this would be 2k plus 2 factorial, 2k quantity factorial, all over x to the 8k, and then we want to start simplifying from there. Now the easiest part here would be x to the 8k. And then I have the absolute value, and I have x to the 8th, 2k quantity factorial, and then the denominator I have a 2k plus 2, which would simplify to 2k plus 2, 2k plus 1, 2k quantity factorial. Now just as a quick note, 2k factorial does not equal quantity 2k factorial, so make sure you have those parentheses in there because that definitely has a lot of meaning here. Now I can see that we have the 2k factorials canceling, and I'm left with the limit as k approaches infinity, absolute value, which it doesn't end up being all that important here because x to the 8th is already positive because it's to an even power. Now as k approaches infinity, I can look at this, and x to the 8th is not changing, k is changing, so I could pull the x to the 8th out front, and then I'm left with the limit then as k approaches infinity. And if I want to FOIL this out, I can. You don't have to, but I'd have 4k squared plus 6k plus 2. I can see that this is going towards 0 because the degree in the numerator is less than the degree in the denominator. You always have to provide the reason there. So x to the 8th times 0 is just 0. Now in terms of the ratio test, does this mean less than 1, greater than 1, or equal to 1? Those are the three things that were important. Now less than 1 means converge, greater than 1 is diverge, and equal to 1 is inconclusive. So this is definitely less than 1. Therefore, what this means then is it converges for all x. meaning it doesn't matter what I plug in there for x, this is going to converge, which means it does a very, very good job at approximating the function. So my interval of convergence is all real numbers, from negative to positive infinity. So there's a lot to this type of problem. And remember, these tables that I have up above that I keep referring back to, you should be able to come up with each of these power series without the use of the table. However, if you have a problem from this particular section that we're working on, I would provide the series that you needed. And again, if you want to have all of those on your index card, that's fine. But please remember, one of the problems might be come up with this. Come up with this correct series using our process. And if that's the case, then what you need to remember is just writing that down won't be good enough. You have to be able to show how that's established. So be very careful about that. It's a common mistake just to have these on a note card and then just write them down, but there's no credit there because we already know what the solution is. Another thing that we can do with Taylor series is we can use these to approximate non-standard angles. For instance, we know cosine is 0, cosine of pi over 2, pi over 6, all that type of stuff. But what if we needed to find the cosine of, let's say, 2? So let's go ahead and approximate cosine of 2, and this is 2 radians, using Taylor series. Okay, so if we approximate using Taylor series, what we would do is we would go up top and we'd find our cosine. Now again, I want to be really clear on this. I guess I already have it copied. If this is a problem on a test and it asks you to approximate using a Taylor series, if I give you the Taylor series, I would say using this Taylor series, then go ahead and use it straightforward. But if I ask you to use the Taylor series that you develop on your own, then you would have to show the work to how this came up. So it's very, very important that you just understand the distinction behind that. Now we would want, because 0 is close to 2, we would want to look at this as a Taylor series centered at 0, and that's what we have here. And so basically for the cosine of 2, everywhere that we have an x, we would plug in a 2. So this would be 2 squared over 2 factorial, 2 to the 4th over 4 factorial, 2, 4, 6 over 6 factorial. You kind of get the idea here. Now a lot of times you'll be asked to use the first 4 terms to approximate. Now we'd want to simplify. So this would be 1, 2 squared is 4, 2 factorial is 2, 2 to the 4th is 16, 4 factorial is 4 times 3 is 12 times 2 is 24. 2 to the 6th, 2, 4, 8, 16, 32 is 64. 6 factorial, quick way to do factorials, if you don't have a calculator, this is more fun anyway, is you can just kind of look at pairings or groupings that look like they're going to go well together for multiplication. 4 times 3 is 12, times 2 is 24, and of course 24 times 3 is 72, so 24 times 30 is 720. And then we could realize that this extends, but these would be my first 4 terms. And then simplifying, we'd have 1 minus 2. 16 over 24, each is divisible by 8, so that would be 2/3. And then for my last term here that I'm looking at, each of these is divisible by 16. 64 divided by 16 is 4, and 16 goes into 72, 64, 80, 16, 45. So minus 4 over 45. And so these would be the first 4 terms, but of course this continues on indefinitely. So it kind of depends on the directions. Now we've already done a problem similar to this, but it was kind of in terms of that second really long problem we did. So I just want to clarify the process here, and we're focusing just on this one thing. So what I want to do is I want to be able to identify the function that is represented by a particular Taylor series. So identify the function represented by the Taylor series k equals 0 to infinity, sum -1 to the k. So I definitely have an alternating series here, x to the 2k all over 4 to the k. Okay, now this k is in the exponent. I want to be clear about that, so 4 to the k. So I'm going to take this whole set right here. Again, if you want to provide this on your note cards, you can. If I want you to use one of the values from this table, I will give it to you. Otherwise, you should be able to develop each one of those on your own. So again, you have to be really careful because the credit's given for developing it on your own, and you need to be really careful about that you know how to do that. So as I look at the different series here, the first thing I note is I don't have a factorial. So if I don't have a factorial, it looks like to me I can throw out this option because there's a factorial. This one, this has an exponent of a k. This one has no exponent of a k. This doesn't have an exponent, neither does this one. So I'm just going to kind of go through and throw out some of these options because they don't really fit that form. This cosine looks like it could work. I have, no wait, that's a factorial. That's a factorial. And this one's not alternating, so it looks like it's got to fit this one. But I do need to rewrite it to make it fit. So let's look at k equals 0 to the infinity. Notice this one doesn't have a denominator. So I'm going to have to rewrite this in a different way. I have the alternating portion, -1 to the k, and then I have x over 4 to the 2k. So this doesn't look too bad. Well, wait, that 4 is not to the 2k though. So I'm going to have to rewrite that as x squared over 4 to the k. Now that fits. So this fits the form k equals 0 to infinity, -1 to the k, x to the k. Now this is equal to 1 over 1 plus x. Now the difference that we have here, and again I got that from right here, the difference that we have here, and I'm going to pull this k out front so we can see that very, very clearly. Our x to the squared over 4 is this x. So what I would do here then is I would replace this x with x squared over 4 to try and come up with that function. Now when you divide by a fraction, you multiply by the reciprocal, but before I can do that I have to find a common denominator and then I can flip it. So this is the function represented by that series. So again, it's just a matter of looking through your list, and then after you look through your list, identifying the function that matches it. So these problems are really fun, lots of good algebra, kind of take you through your paces to see if you remember, you know, all those great algebraic skills and simplification. Make sure if something seems like it's going wrong that you stop and double check your work, because you don't want to get too far into these problems and then realize you have a mistake. Be careful on this one. The habit is to look at the table that was provided to you at the beginning of this lecture, this table at the very top, and then just do the entire unit based off of this. But remember, I expect that by hand you should be able to come up with each one of these using the processes for Taylor polynomials, where we take the derivatives and use that kind of successive process. The only one I wouldn't think that you might be able to come up with might be this 1 plus x quantity to the p, because this is having to do with a combination. So again, be very careful about that. Make sure you don't rely on this too much. Only for this section, no other sections. Good luck.